going to be approaching. Okay,
So
if we do a large number, let's try n equals 10. And we've learned two new tests, one for kind of a general 10 minus 1 over function, minus, and the other one for a particular kind of one function, which is 9 tenths. So the integral test, and there's the p-series. So that's like it's approaching your half, I think. Problem number 3. Says use the integral test to determine the convergence and divergence of the series. So we have the summation from I equals 1 to infinity. So I multiply this by of 9 and this by 10 to the negative n. So to use the integral test, this has to be continuous, which the exponential function is continuous. It's getting smaller. This is actually if we plotted this. So this number looks like it's getting smaller. This, and it's going to approach 0. There's no reason above the x-axis that it's going to be continuous. And so I would say the limit requirement of this function is positive decreasing. Okay, so it's decreasing. If we had e to the n, it would be increasing. So it would be, for one thing, it wouldn't converge at all. One really big number. Okay. So it really passes all the requirements for the integral test. And what it says is that if this converges, so if we integrate from 1 to infinity of e to the minus x dx, this converges, then that converges. Minus 1. Or you can go the other way. If this converges, that converges. And so that's 999,000. So minus use minus x, which is the exponent. So du is equal to negative. You see what happens. This is approaching 1 from the negative side. I'm not going to the lower side. This is approaching 1 from the upper side. Well, I can change the limits if I want to get closer, closer, closer. So I don't even need to do that calculation. So I'm doing u substitution here. So the answer is 0. I could. So what we integrate, u limits are going to be from negative 1 to negative infinity. One more here while I'm recording this thing. 61. Okay, we got one more. So I did e to the u. That was what I just did. Times negative du. Okay, it was 61. So actually, the integral e to the u is e to the u. We have the negative sign, so we get negative e to the u, and the limits are between negative 1 and. Okay, problems 73 and 76. Now the other way we could have done it is substitute back here and get the same. So what we're doing is we're trying to come up with an equation from 1 to infinity. Given the first 4 terms of a e sequence x dx. This one's pretty. So either one. Pretty straightforward. So you can see we start at 2 and we just decrease by 1. We start at 3, I decrease by 1. So the equation is going to be, so I have negative n and then plus 1 up over n to the minus plus 2. And we start at n equals 1, which is the lower limit, like that. So you can see when n equals 1, I'll get 2/3, and then I'll get 3 offs. So e to the negative infinity is 0. And then 76. So if you put in your calculator, 8 to positive infinity, 1 half, e to the negative infinity is 0. 1 plus. So we end up with negative 0, 7, 8 minus e to the minus 1, which is 1 over e. Plus 15, and 16. The negatives cancel out, and we end up with 1 over e as the answer. 31/32. So that is this integral. So obviously we're going to have 1. This doesn't say that this is equal to that one. And what the integral in the numerator we have 1, this converges 7, so since 15. So integral, what I see there is 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1. So what we're going to have is so the integral converges raised to the, well, here we have, when n equals 1, I want 2 to the first power. So let's go to series converges. And then I subtract 1. So make sure that works here. So when n equals 1, I get 2 to the first power. I want to show you. I've never tried this, so I thought when n equals 2, I get 2 squared. Let's go to Excel, and we'll compare the. We'll do this summation thing here, and we'll see what it is. And then the denominator is just going to be this actual 2 to the n. I don't think they're going to be the same. So I don't know if each one of these, the numerator is 1 less than the denominator, and these are powers of 2. New spreadsheet. So there you go. That's it. And I'll share it with you once I've gotten that done. So let's see here, Excel. Okay, so this column is going to be n. And we start with 1. There we go. For quite a ways. We'll go to 50 terms, so that should be fun. 49 terms. This is going to be a sub n, the nth term, which is equal to, what is this function? I already forgot it, e to the minus n. Okay, e to the negative n. So that's that. And then, so we just copy that down. Well, actually, let's go ahead and calculate the first 2 rows that we've copied. So this just equals that value. So that's the first term. Okay, so now we'll copy this to the second line. And then this is going to be equal to that plus that. And then we copy it down until we get to the bottom. You can see that this thing gets small. So we're within 10 to the minus 22nd of the answer. See, it converges pretty quickly. See, 12 terms, we've already gotten 6 digits. So that is the answer. And you do see it does converge. But if I compare the answer, which is I'm getting 0.5819, so let's go back. So from our actual calculation, this is equal to 0.5189. Was it 189? Let me go back and look here. 5819. So it's 5819, which is a number, whereas if you take 1 over e, so 1 divided by, well, actually, it's just e to the minus 1 power. You get 0.367, which is actually the first term. So you can see that the integral of the function that is equivalent to the series is different than the actual series value. So they're not the same. But what the thing says is if this converges, then this converges. It doesn't tell you anything about the value. And there are very few series where you have a nice simple expression for the value. You have to actually calculate it out, just like I did. But for most of our cases, we just worry about the whether it converges or not. And we'll see why that is. We just want to know whether a series is converging or not, whether it's useful. If it doesn't converge, then it doesn't do us any good. Okay, so this is the series. So we got to figure out what is the pattern. So it looks like this number, you're just adding 3 to each one of these. So you'd have 1 over B here. Because you see this, well, not adding 3, 5, 7, 9. So there's a pattern. And the question is, what is the equation that represents that pattern in terms of n? So I'm thinking, So let me stop the recording here for just a second because I need to get it. It takes me more than it'll take me more than a second to think this through. We got it. Okay, so that's what it is. And actually, when you see this thing where you see the difference between being 3, 5, 7, 9, typically means you got something involving a square, n squared. So I think that's something that I've seen in the past. So there's my formula. And so you can see when n equals 1, I get 1 over 2. When n equals 2, I get 1 over 4 plus 1, which is 5. When n equals 3, you get 9 plus 1, which is 10. 4, you get 16 plus 1, which is 17. And then 5 is 25 plus 1, which is 26. Okay, so that works out. So the equivalent function, we would integrate from 1 to infinity of 1 over x squared plus 1 dx. So that is an inverse trig function, the arctangent. So if we integrate that, what we'll end up with is the 1 over a. A is 1 in this case, because I have 1 squared, really. So 1 over 1, the arctangent of x over a. Again, a is 1. If this was x squared plus 3, we'd be divided by 3 here. And then we integrate between 1 and infinity. So now we substitute in the upper limit minus the lower limit, and the angle whose tangent is equal to infinity is pi over 2. The angle whose tangent is 1 is pi over 4. So you get pi over 4. Okay. Again, this doesn't add up to pi over 4. It adds up to something else. But because this converges, because I get a number here instead of going to infinity, then I know if this converges, then that converges. You would expect that this number is getting small pretty quickly. So actually, let's do that with Excel again to see what the actual number is. So let me get rid of that one we just did. Put another new one in here. And then I'll show it to you. So back in the old days, you couldn't really do this with Excel to get a number fairly quickly. But yeah, you can, so it's kind of interesting just to see what the values are. So I'll do 50 terms again. So what I have, a sub n is equal to 1 divided by n squared plus 1. Okay, so copy that down to there, and the sum is the first term, and then the second term is the first term plus this term, and then we can copy it all the way down to the bottom. And so I get the answer is 1.056 something. It doesn't converge quite as quickly as the other one did, but at least we can see it's 1.05 something. And we can actually go. Let's go to 100 terms, just since we have everything ready to go. It won't take too long. I think I did more than 100 terms, but that's fine. Just this is a more accurate result. 1.067. Okay, 1.067.
A bit more.
So this thing is equal to 1.067. Down here we have pi over 4. So we have pi divided by 4 on the calculator. and I get 0.785.
Well, you join us here on TA Outdoors with another build episode. I'm in the woods with Dustin.
And
he's working on a cedar tree over there. I've got my dad here with us as well. And we are building a Viking longhouse. Now, this is not a historically correct Viking longhouse. It's going to be a kind of our adaptation of it.
It's fruitcake or something.
It's leaning up against that tree up there, so it's going to pinch.
I'm doing some
7-inch
more.
Well, right there. Oh, it's rough in there.
The integral test. So we have another one of these where you have to
Fire just down there.
on the moss line, yeah.
Figure out what the equation is. Problem 9. Yeah, it's a little too hard. I'm not going to write them all down. You can kind of see the pattern. So the summation version of this equation is going to be 1 over n square root of n times the square root of n
yes.
plus 1.
Nicely done.
So what's our equivalent function? Integral from 1 to infinity of 1 over the square root of x times the square root of x plus 1 dx. So we are going to make the substitution that u is the square root of x plus 1. So that's a term in the parentheses. So du is going to be equal to, well, before we do that, let's rewrite the square root is a fractional exponent. So you take the derivative and you get that. So you get the exponent, you reduce the exponent by 1. And so we can rewrite that as 1 over 2 square root of x dx. So what we have is 1 over the square root of x dx. So I need to multiply by 2 to get that particular substitution.
Don't know how to treat an old man, do they?
So then what I can, and also my u substitution, so let's change the limits. So when x equals 1, u equals 2. Because I have the square root of 1 plus 1. And when x equals infinity, u equals infinity. Get the square root of infinity, which is still infinity, plus 1, which is still infinity. So our integral becomes infinity.
So we're back at the foundation, and because we did this part without me talking, we just cracked on with some work. I need to explain what we've done here.
2 du. So
these are not going to be the supports to keep the base of the logs together, because realistically these are going to, although we've burnt the end to help get rid of the moisture,
this part is 2
give a protective outer coating,
so
and
it
make
becomes
these,
a natural
preserve
log.
them, make them last longer.
So you get
that
2
they will still eventually rust away, and this will all fall to
natural
pieces.
log.
The only reason we did these stakes like this is so that we could put our foundation together, as you can see around here. Then we could get an idea of what the structure is going to look like, the shape. And we're also going to notch these. We're going to notch them in the corners, kind of log cabin style,
the natural log of infinity,
so that it's self-supporting, rather than being supported with these, because they are going to rot away. So for those that were wondering what these stakes are for, they are a guideline for us to be able to see our foundation, our footprint of the shelter. We brought the 2 big heavy wide logs, as you can see here. These are 10.5 foot, these ones.
Infinity
if we notch
of 1 over
here,
the square root of x times
we're going to lose that much space again, so the shelter's becoming smaller, and we don't want that. So we've actually got some 12 footers over there, which are going to expand the shelter, which means more resources for us to collect, but it means it's going to be a very epic shelter when it's finished. We're going to stop for a quick lunch break, and then we're going to crack on with doing some notches.
To infinity of 1 over the square root of n, square root of n plus 1. Also diverges. Now, the last 2 ones that we did, we saw that it converged. So let's do one here where it actually diverges. So let me put up the spreadsheet, close that, and open up the spreadsheet. Okay, share that with you. n. We have a sub n, which is equal to 1 divided by the square root of that, divided by the square root of, oops, get back here, square root of that plus 1. I think I got everything right, okay. So if we go back to, the first term should be half, which it is, okay. And then the sum, which is what a series does, we take that value, we copy the equation down to here. You see it's getting smaller, so that might lead you to think that it's going to converge, but if we take that there, we get 0.792. Okay. So now I can just copy that down. And so I'm at 3.2522. So, at first you may be led to believe, well, it's getting smaller, so, but just because something's getting smaller we know from experience through chapter 8 that just because it's a monotonically decreasing thing, that it doesn't mean that it actually converges. So that's one difficulty here. I mean, I can do that to 10,000 or 1,000 terms. Let's see what happens here. Okay, 1,037 terms. If I copy that, so even if after 1,037 terms, we're only up to 5.89. You're like, so that thing's, you're saying it doesn't converge. It sure seems like it's converging, but I'm pretty sure that it doesn't converge. And this is actually an answer. This is back in the book, so I can actually look inside the end and bring my book home to do this. So let's just look in the back of the book. I could be completely wrong. If I am, you'll never hear this because I'll fix it. But I don't know anything that's wrong. So it's 9. Diverges. Ta-da! Okay, so there you go. So that's kind of a little puzzling, right? But it does diverge. And there's really no way to prove that I mean, I can keep going on forever, and it's still going to be a number. It's only when you get to an infinite number of terms does this number go to infinity. So it's a little hard to prove from that perspective. Okay, so let's go to the next problem, which is number 12. So we have the summation from n equals 2 to infinity of natural log of n divided by n squared. Now the question is, why did they start from 2 instead of 1? Would 1 work? Because if you do the natural log of 1, you get is 0. The natural log of 1 is 0. So you get 0 over 1 squared. So it's still a number. I think what the point is if you look at the, that doesn't specifically say it, but if it works from n equals 1, then it's going to work from n equals 2 because it's one less term. So we can still do the same substitution. We can still write the equivalent expression, and we can integrate from 2. And so what that's saying is that this has to be 1 or greater. And that makes sense because we always start with, we don't start with 0. Well, yeah, we do start with 0 sometimes. But anyway, it says you have to start with x greater than 1, so x is greater than 1. So we get the natural log of x divided by x squared dx. Okay, so how do we integrate this thing? Well, it looks like an integration by parts problem to me, because we've got two terms. One of them is the natural log, which I don't know what the integral for that is. So what we'll do is we will do integration by parts. So you choose part to be u, part to be dv. And u is the part that is simpler when you take the derivative. So that's the one case, maybe not the only one case, but the major case, where you choose u to be something other than the polynomial part. Okay, so we calculate du, which is 1 over x dx. And v, integrate that, well, this is the same as x to the minus 2 dx. So we add 1 to the exponent, and we subtract, we divide by the new exponent. So this is negative 1 over x. And then we write out integration by parts formula. So u is the natural log of x, v is negative 1 over x, and we subtract the integral of v, which is negative 1 over x, and multiply by du, which is 1 over x dx. So we get negative 1 over, actually, the natural log of x over x, so just combine these two. And we get the positive, the integral of 1 over x squared dx. Well, I just did that, right? It's negative 1 over x. So I'll get negative the natural log of x over x, and when I integrate this, I get negative 1 over x. And I can put my limits in now. Actually, what I'll do is that's the indefinite integral.
Well, that is it for episode 1 of the Viking House build.
And I'll plug it back in.
We've notched out the sort of foundation blocks, really, which is forming the shape of the shelter.
Minus.
Just with some log cabin notches. They're very basic, rudimentary. We're just using an axe. We don't have a chisel. So we just use an axe and a saw. And it's taken a long time. This has taken a hell of a long time. We've just been hammering and axing away, and we've got obviously different size cedar logs diameter here, so it's really hard to get the notches right so that everything's level. So it's not going to be perfectly level.
So the question whether this thing
at the end of the day, this shelter is not actually, the weight of this shelter is not going to be put on these logs. So that's, really, they could just sit on each other and it would be fine. The weight is going to be on the roof, which is the apex sections that Dustin has been building today, which I'll show you in a minute. That's where the weight's going to be on. And even then, it's not going to be too much weight, because we're going for an all-natural roof.
Or does it go to 0?
Going to keep the shingle material quiet at the moment. You'll have to stick around for episode 2, which will be focused on the wood frame, the frame of the kind of A-frame of the Viking House roof. So obviously it's been myself, Dad and Dustin. It might just be me and Dustin next time. I'll try and get that done as much as I can. We are going to use these again.
The limit. So what we should be doing here is the limit.
We are going to be using these burnt stakes, which were essentially our guide stakes, just to mark out the foundation. But we're trying to do this as I say, accurately as possible. We're trying to do this as good as we can with the tools that we've got, which is not a lot. It's kind of minimal. We've not got loads of woodworking tools, but we're trying to keep it as minimal as possible with the tools. So yeah, we're not, like I say, it's not going to be a historically correct Viking shelter. It's going to be our little twist on it. But thank you very much if you're still watching, and yeah, we'll see you soon in episode 2.
Subtracted, so it's all negative. So now you take the limit as it goes to infinity. This goes to 0 versus what I have this close. And just looking at it, you know, which one, does one of these increase more rapidly than the other? Well, the answer is, yeah, this one increases more rapidly, so it should go to 0, but we use L'Hopital's rule here to figure it out. So the limit as b goes to infinity, infinity, and we get an indeterminate result, infinity over infinity. So we take the derivative of each one of those terms. So the derivative of the natural log of b is 1 over b, and the derivative of b is just 1. So that just becomes the natural log of b goes to infinity of negative 1 over b, because it's just this divided by 1 is just the same number. And you see that goes to 0, 1 over infinity, negative 1 over infinity. This goes to 0 from the negative side. So this part is 0, this part is 0, and this part is a number. So as a consequence, and again, we don't really care what the number is, but since the corresponding integral, which was the natural log of n over, did I do it wrong? No, it's over n cubed, isn't it? No, you get the same answer. So I did that one. Actually, it should be x. But I think it works out the same way. So we could go through and fix it. So what do we need to fix in this whole thing? That's cubed. So that's cubed. Okay. So this is 1 over x cubed. Integrate, we get x to the minus 2 over negative 2, which is going to be negative 1 over 2 x squared. Okay, that's the same, and we'll erase that because we're going to fix that. And this part becomes so we'll have that happen again. Become negative, so we get negative 1 over 4x squared. And this is going to be negative 2x squared here. I think that's all right. So we take that back to here. And so we've got 2b squared over 4b and that's squared there. So again, these are numbers. This one goes to 0, And when we use L'Hopital's rule, we're still going to, we're going to have, let's see, that B squared, so you have 4B right there. And what actually happens is, I think we get a B squared here. And so it still goes to 0. And so this converges. And I don't have the answer in the book, so I'm assuming I did it correctly. It gives me every one of them. Let me just check here. Chapter 9. Section 3. Yeah, this is going to be the odd one, so. Okay, so that's that one. I apologize for making a mistake. I'm going to start a new one for this next one. So I'll stop recording.
Put a link in the top of the corner and in the video description below.
Okay,
we burnt all these edges, and the reason for that is that any moisture from the ground, it helps to seal it up and protect it from the rot. It will rot eventually, but it makes it a lot longer to rot away. It gives it that protective seal, evaporates all that moisture out, and yeah, ancient Japanese technique, and is used widely for building just in general as well, building and developments, to help preserve that wood. So we've done that. We've got this is the kind of log cabin style foundation that we've made. Now those stakes earlier, which you saw in episode 1, which
integral would be the integral
here,
from 1.
These have been used as reinforcing points on the joins here, on the joins up there in the other corners, just to keep it all extra sealed, and obviously to not waste the sticks that we've used. We burnt those, we cut them up, we're not wasting them.
Okay, so
they are support sticks, and you can see them kind of dotted around the shelter. There's some over there in that corner, and then some down here, just there as well. For this bit here, this is just to help secure the A-frame while we are lashing it all together, because we've got another one, Dustin's sticking the end one in over there. We've got another one to go in this middle part here. So there's 3 of these large A-frames, and then we're going to lash the centre pole there and some side supports as well. In the meantime, that's what these stakes are for, just to keep it all rigid, to stop this from blowing over to the sides. These stakes are also burnt in as well to help prevent that rot and keep it at bay. But it's looking good. It's looking really good. The Viking house is finally starting to take shape. We're really pleased with the foundations. We've levelled it all off. We've got a lot of work to do still, but it is coming along. Hopefully today, we've only got a few hours left of sunlight. Hopefully today we will finish the actual A-frames,
Let's change the limits,
and
so we're going to end up with
then it will be
U.
ready for the bark roof.
So
How's
the
it going,
integral
Dustin?
of U to U is
We've got some clay down there, so it's pretty hard digging, isn't it?
So we get the
As soon as you
limit
get through all this nice sort of
B
like
goes to
leaf mold,
infinity
yet it's really hard to
of
play.
the integral
I'm sure we can think of something good to do with this.
We've got some ideas, haven't we?
Yeah, a few clay
So we
projects.
integrate it.
One of them actually, to use that clay there, is chinking in these gaps where these log cabin style
let's plug U back
logs
in.
are put together.
So
the foundation, we're going to chink that clay in those gaps, smooth it all off just to stop any draft and airflow going. Just like Dustin's doing there, yeah, we'll work away, crush it all in.
B.
Fill it all in.
Yeah, backfill it with some leaves as well.
Makes it a little bit warmer in the
we use X.
in the longhouse.
It does. It's coming along though, isn't it?
It is.
It's really coming along. Even we've surprised ourselves.
It's taken a few days to get to this.
Yeah.
But we really tried to put a bit more effort in.
Yeah, we're not sort of bodging it. Some areas we are, but things like the dowels.
So now we plug it in
Yeah,
there.
and even trying to preserve the wood. We want it to last for as long as we can. I know it's not going to last forever.
B
we are using natural materials that are all dead anyway.
Yeah.
But things like burning these off, it's going to preserve it. It's going to stop that rot from forming. It's going to put it off by 2 years at least.
Exactly. Yeah. It's coming along though. We're quite impressed. The other thing we did, if you can see up here, today, which took a lot of time, is the wood dowels.
Take the
so we made some holes with a drilling bit,
which is fine. We just
you can see there's the wood dowel that we've used.
We
could have put a wedge in it as well and split it to pinch it in tight and saw the wedge off, but we were quite happy with how that was anyway. And we're not doing it all perfectly. We're just doing as well as we can. So we've got one that side,
squared,
one that side. We've notched out this support pole as well.
And the angle of this tangent is infinity is
so for the roofing materials, which is likely going to be the third episode, potentially the fourth episode, we're not sure yet. We'll see how much we get done here. We're going to go for cedar bark. All the trees that you see around me pretty much here, the evergreens are all cedar trees. The logs that we've used for the foundation, they are cedar,
what we can say
as are the A-frame structure logs. They are also cedar. The bark on cedar is very, very tough. It's durable, it's water repellent, and it's actually one of the few trees that take ages and ages to rot away. It's one up there with some of the best. That's why they use it for log cabin building.
Which means I get an answer.
So it's a very durable, hard-wearing wood. Therefore, so we're going to go for cedar bark. Now that part, or that episode, is going to take a very long time to make. So we may have to merge it into a couple of episodes. We're not sure yet. But that's going to come in time. We are in the winter. It doesn't kind of look it. We've had some rain. We're in January at the moment. We're stacking these episodes up, just ready to drop them for you guys on TA.
Again, they're going to give different answers, but
don't forget as well, check out Dustin's YouTube channel, Bushcraft Tools. He does plenty of bushcraft stuff. I'll put a link to that in the description below. We are going to carry on finishing with this A-frame. Hopefully we get it done today. If we don't, we'll carry on for the next episode. But stay with us.
And 15 converges. Yes. Excellent. Okay. Let's go to 25.
I think it needs to come down this side.
Yeah, that side down a little bit.
So 25 says, use the integral test to determine convergence or divergence of the P-series.
Yeah, you're right.
So we should actually be able to answer this directly, but
yeah, it's PT.
What they're asking for is to use the integral test to prove that this is true. So we get the integral from n equals 1 to infinity of 1 over n cubed. Okay, so the equivalent integral is the integral from 1 to infinity of 1 over x cubed dx. So we take the limit as b goes to infinity of the integral from 1 to b of the same function, which is going to be the same as the integral from x to the minus 3 dx from 1 to b. And when you integrate that, you get x to the minus 2 divided by negative 2, and then it's an integration of 1 to b. So this is the same as negative 1 over 2x squared, so we get negative 1 over 2 times x, which the upper limit is b, and then we subtract, so we'll subtract the negative sign, gives a positive 1 over 2 times 1 squared. And when we let b go to infinity, this stays the same, and this goes to 0. You get 1 over infinity squared, which is 0. So we just end up with 1/2. So since this the function equivalent of the series converges, the original expression converges. Now the p-test says, I think it just depends upon whatever the p-value is. So we look back at the p-value test, and it says if p is greater than 1, which it is, it's 3, then it converges. So this is the long way. The short way is just to look on page 619 and use that rule.
So we've got the front end and the back end of the A-frame up. It's looking awesome. We've also just put the ridge pole on, and now it's really coming together. You can actually see this. We might lift the ridge pole a bit. Yep.
Okay, we are moving on. 28. So 28 says use theorem 911 to determine the convergence and divergence of the p-series. So 911, go look in the book, and that's where it says if p is greater than 1, then it converges. So 28, we actually just did accidentally in the previous no, I didn't. Yeah, 28.
Yeah.
Okay. I'm going to not do that completely. It's really just the same as the one.
What we're doing here, guys, is
for 25.
I showed you this earlier. This is all clay. Because
I'll
it's wet
just
today,
set
it's
it
actually
up. What you'll
compressing
find
quite
out
nicely. If this was the summer, and it
is
was
that
hard,
when
this
you
would
do
be
this
difficult.
integral,
It'd be all crumbly.
Yeah.
But because it's wet, as we bash this down, it's
kind
just
of forms and
it molds. It
so
molds
when
like
you integrate
Play-Doh around
this,
this
and you'll take the
stake
limit
here. So you
as
just see it just getting flat. Look at where
b
Dustin's
goes
hitting
to
it there.
infinity,
It's
integral
just
from
mushing
1
down.
to b.
Amber's helped out with some digging today as well. She's a good girl.
Yes.
Yeah,
What you get when you integrate that, you get.
We are almost
Actually, I'm
there.
going to do it. I'm just going to do it fast, so you can.
And that is
you've
how
already
far
seen
we've
something,
got for
just
episode
negative
2
1 over
of the Viking Shelter,
X.
or Viking House.
When you integrate that
It's looking good so far.
between 1 and b,
We are pleased with it.
and so we've
got all the wood dowels and things,
and
and
plug
the
in
A-frame
the limits,
sections.
so I get negative 1
that.
over b,
That's going to
and
be the
then
entrance
minus
just here.
a negative 1 over 1.
It's all leveled. Look at that. That's pretty
and
good.
when you let b
Given
go
that
to
we didn't even
infinity,
use a
this goes
spirit
to
level
0,
for that.
and this just stays the same,
And that's
and you
pretty
get 1.
symmetrical.
So this
We're very pleased.
converges, therefore
Doing
that
it all by
converges.
eye. So we've left an overhang on the ridgepole up here as well.
Which is 31.
Whereabouts there. So that we
Which
can have a
is the
porch,
P
a small
series.
porch area at the front.
So actually,
It's gonna
given
be good.
a
That's it for episode 2. Hope you've enjoyed
series
it.
that we have to represent.
Make sure you're subscribed. We're going to have episode 3 out possibly in a week's time, where we hope to get a lot more done as well here at the Viking
and since
Shelter.
it's in this
Thanks so
P-series
much for watching,
section,
guys. Really appreciate it.
the first term actually can be rewritten as 1 divided by the square root of 1, because the square root of 1 is 1, and 1 divided by 1 is 1, so they've just simplified that. So what we have in this case is the summation from n equals 1 to infinity of 1 divided by the square root of n. And the square root n is same as n to the 1/2 power. So looking at here, it says n to the p. Well, p is 1/2 and n is just the counter. And it says if p is between 0 and 1, it diverges. Therefore, this original, therefore this series diverges. You can kind of think of it, if you look at the one just on the left-hand side, p here is 2, which is greater than 1. And so this converges, and we proved it using the integral theorem. Here, we could do the integral theorem, but we don't have to because it fits the p theorem. So it diverges as well. In 34, we have 1 over, well, actually 1, we'll rewrite that in a second. So then we get 1 over the square root, or cube root of 4 plus 1 over the cube root of 9 plus 1 over the cube root of 16, blah, 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 etc., etc. So this is also, the first term is cube root of 1. And you see this is n squared, so we can rewrite this as the summation from n equals 1 to infinity of 1 over the cube root of n squared. Which, again, we'll write it in terms of fractional exponents because that's the way the theorem is set up, and we get 1 over n to the 2/3. So this is the denominator, that's the numerator. Again, p in this case is between 0 and 1, so since p is between 0 and 1, the series diverges. Now, we didn't ask to do 33, but let's just look at that one. There you've got 1 over the square root of 2 square root of 2 plus 1 over 3 square root of 3. So In this case, the series is 1 over basically n square root of n, which is 1 over n to the 3/2 power. In the case there, p is greater than 1. So because p is greater than 1, this one actually converges. So I just wanted to show you a case where we had the two problems I gave to you, which both of them diverged. But in this case, when I rewrote this expression, it became a positive exponent that is greater than 1. In that case, the rule says it converges. So this is 37 through 42. We're supposed to match up with these curves. The first thing we're going to do is we're going to answer the question is, does it converge or diverge? And these are all p-series, so all we have to do is determine what the exponent is. So we're just going to look at that. So I'm just looking at the exponent part. So if we write this as a fractional exponent, we'll get that. So since p is between 0 and 1, it diverges. Now, just a second. Okay, there we go. Here you get 1 over n, so p is equal to 1. So that also diverges. It goes between 0 and 1, including 1. So that diverges. Here we'll get something n to the pi over 2, which is greater than 1. So this one converges. Pi over 2 is 1.5 something. Here we have 1 over n to the 2/5, so it diverges. Here we have 1 over n to the 3/2, so that's greater than 1, so this converges. And here we have just 1 over n squared, so this converges because p is greater than 2. So p is between 0 and 1, including 1, then it diverges. So that was these three cases. If it's greater than 1, p is greater than 1, then it converges. Okay, so that's how you would know the convergence. Now what we're going to do to try to match these things up is we are going to try to look at the value of the sum after 10 things, and we're going to use a spreadsheet for that because I don't want to spend all the time doing all those calculations. So let's share here with Excel, and let's create a new spreadsheet. So this is the way it's going to work. We're going to have a column with n in it, like we've had in the past, and we'll go down to 10 terms. And then we'll have, let me insert a column, a row here. So this will be 37. This will be 38, 39, 40, 41, 42. Okay. So those are the different problems. And then you have a sub n, and then you have the sum for each one of those. So we'll take those and we'll copy them. So I'll do Control C, and then Control V, Control V, Control V, Control V, Control V. Okay, now we're going to just do each one of the equations. So this 37, the equation is equals 2 divided by n, which is this number right here, raised to the, wait a second, this raised to the 3/4 power. Okay, 38 is 2 divided by n. 39 is 2 divided by in. Oops, something's wrong there.
Food is good. I'm not going to lie, the food is really good. We just Dustin just cooked up some squid which he caught yesterday.
Last night.
He caught last night some fresh.
Fresher than that.
Yeah, it was seriously fresh squid, really good. If you want to see that video of the squid being caught and everything, head on over to Dustin's YouTube channel, Bushcraft Tools. I'll put a link. It's coming along now. This Viking shelter.
40 is 2 divided by.
We just made a little outdoor fire pit here for cooking. The main project this episode has been the long pit, the Viking long pit, which you can probably just about see over the back there. Just to put it into context, so what we're doing with this Viking shelter is, I appreciate from other videos, I think we've put up 2 episodes so far, and I probably need to explain a little bit more in this episode about what's actually going on, because there's a lot of new people on board, which is great, so I appreciate that. But yeah, I'll just give you a bit of context. So we're in a private woodland, Dustin's woodland. The wood's already been pre-cut. It's all cedar wood, it's cedar trees.
42 is...
So to answer some of the questions, why didn't we strip the bark off the bottom of the logs?
Squared.
The reason is because those logs aren't actually taking any weight at all. So
is going to be,
cedar is very rot resistant as a tree. They will take a very long time to rot away. It's the actual frame itself, the A-frame. That's what's taking the weight of the shelter. We haven't done the roof yet. I think I said in a previous episode that I was going to do the roof. Or we were going to do the roof, sorry.
So that's the sum.
We're not going to do that now because we figured if we put the roof on, it's going to make it really restrictive inside to do things like the fire pits and the beds and everything like that. So we figured maybe actually with the roof as it is now, with with the frame there, but not the roofing material, then we can actually do a lot more work and move around a bit more and dig and stuff, and just get things built in the shelter and then put the roof on. I know it's just probably a strange way of doing things, but it's just kind of the way we've ended up doing it. So we're digging down about, say, a foot nearly with this fire pit. We're going through the soil layer. It's a bit peaty. We're going through the soil layer and into the clay, and there is so much clay on this ground, which is brilliant because we've got so many projects that we're going to do with this clay. So we're going down to this clay layer, about a foot deep. We found the stones that you see in the video, the footage earlier. We actually found those lying around in the woodland, which was awesome. We were quite surprised at that. We thought we'd actually have to either go and get these stones elsewhere from somewhere else, or just try and source them from further afield. But thankfully, they are they're here. They're in this woodland. We're running out though. There's not many left. So the plan for this episode is to try and finish the fire pit. We are now 4 o'clock. It's winter. So we've got about 40 minutes of light left before the sun sets, and then we've got a little bit of twilight till about 5, and then it's going to be dark. Yeah, so I'm hoping that answered some questions, that why we didn't peel the bark off the bottom logs. I know that peeling the bark off preserves the wood for much longer, and if you're doing traditional cabin building or any kind of long-term structure, you should always peel the bark off. But I thought I'd just explain that to you why we didn't peel the bark off. It kind of looks a bit more
in the column here.
Rustic, I guess, with the bark on. For the beds that we build in there, we probably will strip the bark off those, just so they do last a bit longer. A few of you said about where we've put the saddle notches on the ends of the corners to drill a plug, basically, a dowel into those to stop those corners rocking. So we're probably going to do that at some point. We did use the rest of those sticks in the previous episode to cut down level and just secure it all a bit more.
So there's that.
The other thing was, which I learned in the other video, was the bit of brace I was using. I was using a flat bit. We're not experts here at all by any means. We're complete amateurs at what we're doing. So I appreciate for you serious woodworkers out there who are watching it. It must be quite painful, but I apologise for that. We are just out here having a bit of fun, trying to enjoy ourselves, and we're learning along the way. The bit brace bit, I was using a flat bit, the drill bit, and it was difficult. It wasn't easy. We did drill the holes with it eventually. Got a nice bruise on my chest from leaning on it. So I've got some tools.
So these are the numbers I'm looking for.
So I've got an auger coming in, the barrel-ized Scotch augers, which is obviously going to be a lot better for drilling holes in wood. We're going to make other things around the camp as well.
Find out which one's which.
What else did I get? A draw knife. I've got a draw knife. to be able to strip some bark off things, and just some other smaller tools, because we've used really basic rudimentary tools.
They're far enough apart
basic
to
structure.
tell which is which.
If you guys have any suggestions on other tools,
so
maybe to
probably the most
have to
obvious
help build
one.
this structure, I'd really appreciate it.
Where it goes to 11.
That'd be great. For those people
and
who
that looks
we
like
had a few
it would
comments
be
of people
A.
saying it's nothing like a Viking shelter,
So this
and
one
I
looks
do
like
kind of understand what
this
you
one
mean,
must be A.
because really it's not a traditional Viking shelter by any means.
Okay, the next smaller one is
I guess
7.5,
when I speak of early Vikings,
we
I mean
go
the very
there,
kind of
look,
original
and
Vikings.
it
I think
looks like
Vikings, I believe, was a bit more of a word to describe
that
the
would be
people
C.
who travelled and raided and covered ground and made buildings. It wasn't necessarily
and
just
the next one is
a
5 point
typical person. It was just
something.
what they did. It was almost a thing of what they did.
So which one
But
is to 5?
Early Vikings used any
Like
resources that they found in the area. Anything
Okay,
they would
we
use to help build their structures. So
3.99.
for Scandinavian type areas, they used logs. They had plenty of trees over there, so they used lots of logs, and they had much more log cabin style in a way. Big structures,
So
big long
we know
houses.
that
Some of them I think were up
is
to over 250 feet.
this one.
So really long,
That's
big
the
structures,
lowest one.
almost like medieval halls.
The
They
question
were
is
massive.
between these two. That's
But over in Iceland, they have.
that's the one that
They
might be
didn't
more
have all the
difficult.
trees like they did in the
So we're
Scandinavia.
comparing what
So they
we
used
got
sod,
A,
they
B,
used turf, and
A,
the houses
C,
were kind of much
E, F.
lower.
So
The pitch of the
B
roof
and
was
D
much lower,
are the
and they
two.
just used turf. They used peat
And I
blocks
think
and sod to create their shelters. So they were really resourceful, and they used whatever
they're
they
so
can. So
close.
I appreciate that this isn't
Trying
an
to-
official
let me just look at
Vikings
them
shelter.
straight on
If
here.
anything, it's got a mixture of Anglo-Saxon in it as well. But we're just
Thinking
working with
that-
what we've got, as the Vikings once did, trying to build where we can, and just learning. We're constantly learning.
The
So
larger one
thanks
is
to the guys who are
probably
giving
D,
feedback that's constructive.
just because
We
of the
appreciate
scale
it.
they used.
We're going to carry on
So
with
this
this
is
fire pit
D,
build now. Possibly
and
eat
this
some more food.
is
We'll
B.
run through the food quickly, just what we've got. Dustin, come over here. What have we got?
Well,
We've got Amber
So
with us as well.
that's
Explain what we've got here. This is amazing, this
So
dish.
they're
what we have
C, F,
is
D,
breadcrumb
A.
calamari
D.
rings.
Look
Amazing.
at these. And this was
So
caught,
fresh.
yeah, so fresh
go
from
back.
yesterday. Not even a day old, not even 24
far.
hours old. And Dustin's cooked this up. And I can tell you now, guys, it's ideal to mould, and we'll just
down.
bash this all down. We're going to clear this
So
out a
this
bit
one
more. We've
matches
still got
up
some
with
to put here.
C.
And we're actually going
matches
to
up
have
with
some
F.
stones kind of
So
up
matches
here
up with
on the
B.
top of the
So
pit,
matches up with
buried
A.
down level so it's all level.
So matches
That
up
way
with
when you
B.
walk across here,
Matches up
you'll almost
with
be
B.
walking across some stones and things
Yeah,
like that
so it's good
across
in the
here.
back of the book.
And it'll all be
See if
levelled
we
off. It's going to
can,
take some time. We might not be able to do it all in this episode.
Figure
But just
out which one
imagine
is
and
right
picture a
here.
lovely, big, long fire here.
It's
Two
37.
kind of benches this side and two raised beds this
So
side. A little
37
bench,
says
workbench at
C,
the back
and
where
the
we
diverges.
food
Okay,
prep
good.
and everything.
38 F.
Oh, it's going to be
diverges.
amazing.
39
We'll have a little opening in the top
B
here so all the
converges.
smoke can come out.
40
We've
A
got dessert.
diverges.
What's this? Some melon.
41 D
Watermelon.
converges.
Mm.
42
We're going
B
to add some more
converges.
cooking
Hey,
to
that's
the
right.
episodes as
Right.
well. So if you're still watching, we really appreciate it. Thanks, guys. Stick around for the journey. Subscribe.